start recording. All right, guess most of you are here. So today, I think, we are going to switch gears a bit. So far we talked about telemetry systems for networking. What we're going to talk about today and next few lectures is still related, but a bit more, like comprehensive about how exactly the telemetry systems are getting used and the differences between different type of telemetry or analytic systems that are related to networking, right? And how exactly all these systems can be used to develop and test AI and machine learning models that are relevant for networking. And we will also talk about why do we really need AI and machine learning for networking. Okay. All right, so before we move forward, just a quick recap. Sonata, we talked about Sonata as a network telemetry system. Sonata is a hybrid telemetry system, which is that it is basically using both the hardware switch and stream processor to execute the query. The key contribution that Sonata has that it is both flexible and scalable, that it is not compromising on type of queries you can express. And then it is just figuring out ways in which it can scale the execution of those queries, leveraging both the switches and the stream processor. And maybe the last 2 points are not as interesting or useful for you, but I think just to give you a sense that Sonata is just a small step in a bigger research agenda about building these type of systems. So Sonata is good, but it's not so good. It's not able to handle dynamics, both in terms of the workload that is handled by Sonata, and also the type of or the workload in terms of queries that it can execute run, right? So moving on, I want to talk about the use of network management or network telemetry and how is that related to network management, right? So if you remember when we were talking about telemetry systems, I mentioned that the network operators are interested in figuring out what really is going on in the network, right? So they want to understand the state of the network. And then based on their understanding, they make some decisions about the network. For example, if they identify that there's an attack going on somewhere in the network, then the type of action that they want to take is to block the attack traffic, right, at appropriate location. So in that context, it is still the case that the network management is still very human-centric, that the network operators are the key players when we talk about network management. They are the ones who are deciding what type of queries or tools need to be run. They are responsible for analyzing the output of these queries and then deciding that what type of configuration changes are right in the network, right? Like if it requires blocking traffic, then they have to write a configuration saying, hey, block this type of traffic, right? So, like specifically talking about blocking traffic. So, that is where the software-defined networking is useful, that you can specify these flexible control policies saying, hey, I want to block this specific traffic, attack traffic coming from a specific set of sources, right? So this is the flexibility that SDN already offers. You can imagine, B4 and all those systems that we talked about, SPXs that we talked about. So that's for the control part. Sonata that we discussed, or all these range of telemetry systems that we discussed are all about the monitoring part, right? And these two set of systems in conjunction are responsible or are aiding these network operators to make sure that they're able to make these right decisions and handle these different type of tasks, right? So when the network management is so centric around human operators, we have to take into consideration that there are certain type of things that human operators can do well, and there are things that they cannot do so well, right? So one, they have a lot of insights. They have been running these networks, so they have a lot of contextual information when they see the data. They have a good sense of what really is going on, right? So that's one good thing about having networks, but they are only good at identifying some simple, patterns in the data. Also, only when the network events are really huge, right? Say, for example, an outage happens or a cyber attack happens, then the entire network is affected. The signals about those type of events are strong enough that it's there. If you have the right tools, it's really hard to miss that, right? So only when these network events that we are talking about are very prevalent, their coverage or their impact is huge, then only these network operators will be able to identify those type of events, right? And then, of course, if these events are happening at much higher frequency, then the operators will just get overwhelmed. It's not really possible. Only when these attacks are happening once in a day, once in a week, then it's okay to have this type of framework. But if the frequency of the events of interest is just increasing, then it's really, really hard to have human operators in the loop. But now we know that the requirements in the networks have changed dramatically in recent years, right? So, the model that I was explaining earlier is fine if you're talking about a small network, say UCSP. If you're talking about the type of network like requirement that we had here, maybe a couple of years ago when we were not really intense on Zoom and YouTube and all these different type of applications. But as we have seen that in recent years, there has been a significant increase in the usage of different type of networked applications and devices. The requirements that we have from the networks have intensified significantly, right? And let me give you an example, and then we can reason about why I'm saying this. So, as you know, that video conferencing applications like the one we are using right now has gained a lot of traction right now in terms of usage, right? Like if there is a big outage happening somewhere in the network, everybody will know that Zoom is not working, right? And maybe that's an easy task that a network operator can handle very easily. But what if I say that some type of disruptions happen in the network all the time, and applications such as video streaming and others, they are capable of handling those type of dynamism because they have some buffers and all those things in place, right? But video conferencing applications, these are real-time applications. They don't have that type of flexibility. So even if there is a disruption happening in the network, which is as small as few seconds, you will see that impact. Sometimes you will see some freezes on the Zoom. Sometimes you will see, like audio cutting off at times. These are the things that happen all the time, even in a network as well provisioned UCSP, right? Think about the networks at, like some of the home networks, cable networks, where the network is even more congested and more intense. And we see these type of events happening there even more often, right? So now if I put these old set of tools and techniques that we have been using as a network community, the type of tools which maybe like are capable of identifying only coarse grained events and not capable of identifying these small scale short-lived type of events, then we might not be able to identify these type of events, and then effectively we will never be able to react to these type of events, right? So overall, the shift in recent years has been that the requirements or the type of events or like activities that the network operators really need to handle are much more complex, right? It's much more subtle, and they are not wide scale. These are small scale events, right? Like when the disruption happens, it might just happen in this location or maybe just in your laptop, right? So like these are not large scale events that the signals will be so strong that even if you use very nice set of tools, you'll be able to see, okay, there is some problem in the network, right? So these events will happen and then just go away and you will never know about them. But there will be unsatisfied users on campus who will complain that I really didn't have a good experience watching these Zoom videos. And then network operator will have no say or understanding of, like I'm talking about from real experience. I talk to network operator here, we talk about, hey, like, these are the things that we are observing. And it's like, no, I run a Zoom session, there's no problem, there's nothing wrong, right? So network operators can only handle or identify things that are relatively persistent, have a much, much larger impact on the network. Anything that is so subtle, so small, so locally scoped, they can't detect that, right? And another thing here is that, these things, these disruptions that I talk about are very frequent, right? I'm not talking about once in a week, you will have issues on your Zoom sessions. I'm talking about every few minutes, you will have some type of issues on your Zoom session. You might be severely affected by that, you might be marginally affected by that, but most of you are affected by these things, right? And Zoom is like one just such application, but there are so many real-time applications that we're talking about where any type of network disruptions can have a significant impact on your user experience, right? So now the question is that what do we do when we know that the network operators are not really capable of handling these type of events and they can't really optimize the network or optimize the user experience given these type of events that happen in the network. So what has been going on in the networking research community is that they have been internalizing that, hey, network operators are pain. One, we have to pay them a lot. And two, they're not really good at identifying these subtle patterns in the network. So let's replace them with machine learning models, right? Let's try to use systems like Sonata or a bunch of other systems to collect the right or high quality data from the network, do all this apply state of the art machine learning algorithms and identify or detect these type of patterns, as subtle patterns that are going in the network, and then decide what needs to be done, right? So there has been a lot of effort going on in this space in past couple of years. I'm just naming few players who have already publicly announced that they're working on various range of projects which are applying or developing AI and machine learning based solution to optimize the network management within the network, right? In fact, I just was participant at the annual research summit at Google, which just concluded a couple of hours ago. And Google just laid out a much more elaborate plan of how they want to build autonomous or self-driving networks that are going to optimize or automate the configuration management for them, such that they can handle all these different set of wide area network issues that we were talking about earlier. So they want to use SDN as the control plane, but they want to use Sonata-like systems to extract insights about what's going on in the network, and then automate this loop or close this loop in an automated fashion, right? So this is just one example of what's going on. Companies like Verizon and AT&T are similarly interested. For example, AT&T is interested in optimizing their 5G networks, where they want to first identify whatever traffic they're trying to deliver to the customers. First, they want to identify which traffic belongs to Zoom and which traffic belongs to Facebook and all those things, right? You can think that this must be super easy thing to do, but given most of the traffic is extremely encrypted, and most of the traffic is coming from the same set of CDNs or content providers, then it's really hard to discriminate based on the source IP addresses of this traffic. And you really need automated tools and techniques to figure out that which set of packets belong to which application. So that's traffic classification. Once you know something about traffic classification, then you need to know that, okay, if this is Zoom session or a YouTube session going on, then what is your current user experience, right? What is the resolution that you're looking at, or what is the buffer size? Maybe buffer size is a too detailed concept for you to understand, but I think when you're watching these type of video streaming sessions, there is always a buffer that is created where it's downloading some chunks of data and then playing it for you. The size of the buffer is in some sense a loose indicator of your user experience. If your buffer is almost empty, then most likely the video will freeze and you will have a bad experience, right? So that's why buffer is used as a proxy of your user experience. So if I want to make some decisions about how should I handle a particular stream of packets, I need to know that one, what type of application you're using, and then I need to know that what is the state of that application right now, and then I can make some decisions. Say, okay, I observe that your YouTube session is suffering because you are not getting as much bandwidth as possible. Then I might and someone else's buffer size is extremely high, so I know that they can tolerate some low bandwidth for next few seconds. I can use that bandwidth and give it to you, right? So this is a scheduling decision that the network operators really want to make, and these type of decisions are made at the radio access layer for 5G networks or 4G networks, right? So these are really, really hard problems if you want a network operator to be involved in making each and every of these decisions. So there is a consistent trend that everybody is just focusing on that. One, we should collect the right quality of right high quality data from the network, train machine learning models, and deploy them in the network, right? But a bigger question out there is that, this is all exciting, but if you are not Google, Facebook, Verizon, AT&T, or Alibaba, then what will you do, right? If you want to develop a machine learning model without in an independent manner, there is no way you can participate in this type of work, right? Because the most important thing that is required to pursue this direction is that you need data to start with, right? And if you are not any of these entities, then it's really, really hard to participate in this. And you might wonder that why is that problematic? These are the people who need it, and these are the people who have resources to work on these type of problems. Why bother about it? I think there are a lot of societal impacts that can happen if we do not engage a broader community in this type of research, because all these machine learning models will be black box models that you will have no idea of how they work and operate, and then they will be making decisions affecting your quality of experience or your experience in general, and we will have no accountability of how these things really work, right? So overall, there is a much stronger case to be made that we need a broader participation of the bigger community working on this research direction, given how important and critical it's going to be in the future, right? But unfortunately, my assertion is that we are not really ready for this type of transition. We are not really ready or prepared to explore or develop new machine learning models that can optimize network operations in general. And let me try to make that case a bit more clear to you with a more specific example. So this is a real problem that I've been working on with my collaborators at Verizon. And like before I go into the details, I just want to tell you that this lecture is basically a mix of what you have learned so far and how that is getting applied in real world right now, and what are the open challenges, and what are the like technical problems that the community is trying to face right now, right? So this is a sample of problem that we are working with Verizon, and what's going on there is that whenever you are connected to Verizon, it's on their 5G or 4G network, then all this traffic is going through the radio access network through the core of their network, right? And at their network's core, they have these farms of servers that are basically doing intrusion detection or doing firewalling on the traffic that is coming in and out of the network, right? And they really want to make sure that they are able to process all this traffic so that they can identify malicious traffic in the network. They identify any type of attack that is going on in the network so that they can secure and provide safety to all the other users as well. But this entire process requires stateful packet processing, right? And as we have learned before, that stateful packet processing is expensive, right? Especially when we're talking about terabits of workload, stateful packet processing is an expensive thing, right? In a sense that, we know that you can try to do stateful packet processing in the hardware. Maybe that will reduce the cost, but it depends on what type of stateful processing we want to do and how much stateful processing we want to do, right? Because stateful processing will require memory, first thing, right? We have limited memory in the hardware switch. And then stateful packet processing might also require deeper packet inspection, right? And we know that it's really, really hard to use commodity hardware switches to dig deeper beyond layer 4, right? TCP UDP transport layer. Going anything beyond that is extremely hard with a hardware target, with a commodity hardware target. Of course, you can use specialized hardware target, but that just increases the cost. So the way these type of networks really work is that right now they have not embraced the hardware switches, right? The ones that we have been listening or learning about. But there is a process that these things are we're working with them. We're trying to make sure that they understand the value of these hardware switches and try to adapt their network and use these type of systems. But while they're not using it, they're relying on these user space servers to support these IDS firewall functionalities. Okay. And as you can imagine, when you're talking about terabits of workload, it's going to be extremely expensive for them to scale everything, right? And there are two ways you have to think about the scalability here. One is the complexity of the stateful processing that they're trying to do, right? So if they just want to do one query on the data, that's relatively easy thing to work with, right? But if they want to cover all possible rules and combinations and signatures on the traffic, then we're talking about hundreds and hundreds of rules or queries that they have to run on the network packet. And imagine doing that at the terabits TBPS workload, right? So this is an extremely, extremely challenging thing in terms of scalability. And we are talking about, hundreds of millions of dollars worth of investment to go from 100 Gbps to 200 Gbps and 200 Gbps to a couple of terabits per second, right? And as these mobile ISPs are in a bit of a transit phase or transitionary phase, that they're switching from 4G to 5G, and maybe very soon they'll be switching from 5G to 6G. Each of these generations are just intensifying the amount of data that they have to handle, right? So when we were talking about maybe 3G, they were talking about few tens of gigabits of traffic that they were handling on their core. And now the set of functionality that are being supported with 4G and now 5G, they're expecting a workload of terabits per second. And right now they're not able to handle it, right? So right now the operational decision that these operators, at least at Verizon, that they're made is that they're not sending user traffic to these IDSs, which means that any traffic in and out from their mobile network, which belongs to mobile phones or users in general, that does not go through the IDS. And this is something which worries everybody, because like you really want to be cautious about the type of traffic that is coming in and out of your network, right? So this is a bit of a risky situation we are in, but the fundamental reason why such a decision has been made is because it is so extremely expensive to build an infrastructure that can handle these things at terabits data rate, right? And this data rate is just going to increase. The complexity of rules or queries that you want to run on these type of traffic to understand, like whether they are malicious, whether there is any type of malicious traffic or malicious packets in the network, that is also going to increase, right? So we're just expecting all this thing to just get worse in over time. And the naive approach of taking in all packets and then applying these expensive packet processing on each and every packet is just prohibitively expensive, right? So what can we do? Like, the idea that a lot of researchers, this is not a new idea at all. People have been looking into this problem for a couple of decades now, right? So people started thinking that, hey, like when we think about an intrusion detection system, what is it doing? It is looking into sequence of packets. It is doing a deep packet inspection, which is basically extracting a lot of payload fields as well from the packets, and then it is maintaining certain amount of state, like it is checking for different type of attack signatures in the sequence of packets, right? So more signatures you are checking against, more complex the packet processing pipeline is going to be, and more deeper fields you are trying to extract and check on, right? So the more expensive that pipeline is just going to be, right? So this has been a problem in the community for a while, and the observation that a lot of researchers made was that, like by definition, we're looking for anomalies in the network. And when we say anomalies are always rare, right? So the other way of looking at it is that, the traffic of interest is a very, very small portion of the total traffic. So if we have some mechanism, some ways in which we can maybe look at the behavioral patterns that are exhibited by these IP packets, especially focusing on their header fields, not the payload fields. If we can identify a certain set of patterns and like formulate that as a machine learning problem, extract features from the packet headers, frame that as a machine learning problem, and then compile that machine learning model, or at least the decisions for that machine learning model, into the hardware switch itself, then we might be able to filter out traffic that is definitely benign, right? That is definitely not going to do anything on the IDS, right? So this is the idea that a lot of researchers have been flirting with in recent years. But the original set of ideas go as back as like 1999, when there is the first evidence of this type of research going on, right? So and now that we understand how, say, packet processing and PISA switches work, how systems like Sonata are able to extract different features or run these type of queries on the network traffic in the data plane itself or at scale, we understand that extracting these features from packet headers is feasible, right? And then encoding those decisions as machine learning models is technically feasible. And there is a lot of work going on, which I probably won't have time to cover in this class, but there is a lot of work going on in terms of figuring out how we can compile a neural network into the hardware switch, right? So we learned about how we can compile data flow queries into the hardware switch with Sonata, but there is more recent work going on which is trying to figure out, how can I compile a DNN onto a hardware switch? How can I compile something as simple as decision trees on a hardware switch? So there is a lot of work going on in this space, right? So technically, it is feasible for me to compile such a machine learning model into the hardware switch, and if I do the right job, if I do a good enough job, then I might be able to offload a lot of traffic from going to the IDS, right? And that will be significant gain from the scalability perspective. But so clearly, I have probably motivated you that machine learning in context of this problem is a very powerful tool to apply, right? And as I said, like these people have been flirting with this idea for a couple of decades now. So there are solutions to this problem. But what has been the approach as a solution to this problem? The approach is that let's use some synthetic packet traces that are out there, which are mostly collected in a control settings in an active manner, right? So maybe I should unpack you like what this really means. So there was this research competition that was launched in 1999. It was some KDD IDS challenge something, right? It was basically launched by DARPA back then. And the idea was that they were like running this in an enterprise network and they were actively sending some attack traffic to the network, right? And then mixing the attack traffic with the normal traffic. And they released that data set. And the challenge was that, okay, come up with a machine learning model that can help identify the attack traffic from the benign traffic, right? And this is something that has been, like the data set that a lot of researchers have used for past 20 plus years. And then in in late 2010s, there were researchers in Canada who argued that, whatever DARPA's data set was, KD data set was, it has XYZ flaws. So we have a better mechanism or better methodology for collecting data set. And then people have just shifted their focus to their data set, and they've been developing machine learning models using that data set, right? So what happens in these type of control settings is that, they have bunch of servers that are benign, bunch of servers that are, attack servers, and then they launch that the malicious servers basically launch attacks to the benign servers, and then they do a packet capture, and then they use those packet captures as the data set that you can use to infer or develop machine learning models, right? So this has been a very active area of research, and something as recent as ACM CCS 21. So again, this is a very, very highly reputed research conference. This CCS is a research conference for network security or computer security in general. So this is not really just a networking paper, but it talks about a problem related to network security, right? And the key idea that they have is that, when you have these packets, then you should translate those packets into something very similar to packet header vector, right? So like the packet header vector that we learned about in the PISA switch. So what is unique about the packet header vector there is that every packet field has a specific location, right? So there is a specific set of bits that will always represent the TCP source port, TCP destination port, UDP source port, UDP destination port, irrespective of whether the packet is UDP or TCP, right? So there is a one-to-one fixed mapping for every packet field. So this is the similar idea that nPrint ML research also focuses on. And they argue that such a standard representation is required so that you don't have to retrain the model depending on what type of fields the packet has, right? So you have these fixed set of fields, and then you can just, like, once you have the standardized representation for any type of network packets, then you can apply state-of-the-art machine learning tools on that, and without requiring you to change the models if the type of packets have changed, right? So this research work, when applied on the synthetic data sets that I was talking about earlier, they give you excellent results. They give you results 99.2 F1 score, right? So F1 score is is a proxy for accuracy, or is a metric to quantify accuracy, and it shows that this type of model has a very high precision, very high recall. Fantastic, right? So maybe if I look at this result as a network operator, I'll be convinced maybe I should just use this machine learning model, and that's going to solve my problem. 99% of time I'll be able to successfully detect benign traffic in my network, and I will be able to, with high confidence, let that traffic go, because I think that traffic is not worth sending to IDS because it's all fine, right? But life is not that easy. So what other set of researchers did was, well, maybe I should not refer that. What we did was that we picked that machine learning model. We collected data from UCSB for 10 hours, right? And we curated a data set which is not active, which is passive, that we are just focusing on just capturing the data, and if there is an attack, then we just add label to it. If there is no attack, then it's benign traffic, right? So we did that for 10 hours, and we repeated this for multiple set of hours as well, but I'm showing you the result for 10 hours. And we use another tool called Suricata. So Suricata is a tool which is is used as an IDS by a lot of enterprises. So for example, Verizon uses Suricata as a tool of preference for doing the IDS task, right? And so we use that to label the packets and flows. If there is a, Suricata has a list of rules. It has rules for what is the DDoS attack traffic looks like, what does the port scan traffic looks like. And then in the 10-hour packet traces, when it identifies that, okay, these set of flows are doing port scan activities, then it will label that as, okay, this is a port scan flow, or this is a DDoS flow, right? So this is what the data set is. And then we apply this type of the nPrint ML machine learning model that was giving 99.2 accuracy on the synthetic data set. We observe that the F1 score for benign traffic to detect benign traffic is 0. It's not 70%, 80%, 50%, it's zero. So, like what we're talking about here is the state of the art artifact that is out there in the research community. And if I just use a production data from UCSB, it doesn't work. So there is no way I can have confidence in any machine learning model that is trained using these synthetic data sets, because maybe there is a problem in this type of data set. And that's precisely what we tried to explore as well, that the nprint, like we analyzed why this model is making these type of decisions. And we learned that the way nprint is making its decision is that it is vulnerable to shortcut learning. And now you might be wondering, hey, I don't know what shortcut learning really means, right? So shortcut learning is a problem in machine learning, where rather than trying to identify a specific attributes of the problem at hand, you just learn some shortcut ways in which you can differentiate between, or like make distinct decisions based on some easy features that have nothing to do with the original data set, right? So maybe let me try to explore that a bit more. So let's try to visualize that a bit here. Suppose I give you an image and it has star and it has moon, okay? And I give you another one which has star and moon, okay? Like this is just one simple example. If I ask you that go and train a machine learning model, what do you think the machine learning model should do? If it wants to differentiate between star and moon, what should it do? Look at the shape, right? So shape is something that we intuitively know is different between star and moon, right? But if I give this data set, what a lot of machine learning models can do is that they can identify that, hey, in this data set, star is always towards the left side and moon is always towards the right side, right? So it will just look at, whether there's something on the left side or something on the right side, and I give it an image and it will say, like, if the test data which I'm giving it as input, then it will, like, if it is following similar distribution, then it will be doing a fantastic job. But the moment I put star there and moon there and star here, then it will just mess up, right? So this is an example of shortcut learning. It just made an easy choice that, okay, let's try to put a line here and just look at these specific quadrants of like what, like, whether we have something in that quadrant or not. And if there's anything in that quadrant, we can just say there is a star, right? Irrespective of learning whether it follows the shape of a star or not. So it is a problem with the data set, right? So the machine learning model is probably not so bad, but it also is an artifact of how exactly, like, so I won't say it's a problem with the machine learning model, but it's a problem with the pipeline that you're using to come up with the machine learning model, right? So if you have enough robustness mechanisms in place to check, like perturb the data and, make sure that you are ensuring robustness across different type of distribution, then probably you will be able to do, address this problem. But in general, yes, this is considered as a problem with the data set itself.
Like what shortcuts enter them all down?
Yes, I mean, like, it's not public, but it is known. So, if you're more interested, I can talk about that offline, but, like, this is an active area of research right now. It's not just the nprint ML that we found problems with, but almost all cybersecurity machine learning artifacts that are out there that are using some type of synthetic data sets or not using production data sets, we found problems in them. The problems were either they were, victims of shortcut learning, or we found that they were learning relationships that are, that should not exist, or they are, like vulnerable to out of order distribution issues, which is like, which is also the case for the synthetic data sets, that when you look at the features, the type of distribution for those features are completely different from when you have a production network, right? So sometimes some models are robust to those distributions, sometimes those models are not, right? So we observe that even the state-of-the-art machine learning models that people have just internalized are perfect and fine. With this type of data set, we realize that none of them really work. Okay. Yeah.
The 9 data list is like F1 score zeros. I mean, I think that's everything is stack tracker.
Yeah. All right. So now I think, like, we need to really question that if we want to build a machine learning model, which is going to solve this network management, network operation problem, and something that we can trust to deploy in production settings. What do we really need? We need high quality data, which is very critical for developing robust machine learning model. But there are certain attributes that the data has to satisfy. It's not just that it has to be fine-grained or packet level data. It has to be labeled, of course. It also has to be longitudinal and representative. So what does it mean longitudinal? Anybody wants to take a guess? What does a longitudinal data collection means?
It's like every type of attack traffic. It's not just the last.
Right. So and how we can ensure that is that we collect data long enough that it captures all sorts of distribution that are possible in the operational environment, right? A lot of time when networking researchers try to do machine learning projects, then they just collect data for a couple of hours, couple of minutes, train machine learning models on that, show results, and they're happy, like, okay, I got 99% accuracy. But that's not something that we can trust, because it's just overfitted to a certain type of distributions. And as soon as those distributions change, then those machine learning models are not going to work, right? So we will not have confidence on those type of machine learning models, right? So this is a, I'm not saying that there is problem with the researchers or their artifacts. I'm saying there is a problem with the process, right? So every time a machine learning, every time a networking researcher tries to develop a machine learning model, what they have to do is that they have to think about what data they need. Then they spend a lot of time developing tools that they can use to collect that type of data. And then maybe after that, 20% of time effort is just, okay, let's pick some state-of-the-art machine learning tool, apply it, and show that it works, right? But that is something which is problematic in a sense that what we really need is that we need this high quality data that is longitudinal, fine-grained, labeled, and everything. We also want to road test all this thing, but this all takes so much of effort that if we try to repeat this for each and every new artifact that we want to develop, then we will always be focusing on just data collection and testing. We will never focus on the machine learning model itself. We will never focus on these robustness type of issues. And that is what is reflected in our analysis of existing machine learning artifacts as well, that none of them really work because most of them just focus on data collection issues and very, very superficial problems related to the area, right? So this goes back to my initial assertion that even though there is a very clear need for developing machine learning models for network problems, even though there are players in the industry who are actively working on developing these machine learning models, the broader community is not really prepared to work on this. And the biggest reason is that we don't have the high quality data that is required to develop these models, and we don't have an infrastructure or test bed that we can use to road test these type of machine learning models in production settings or realistic settings, right? So what can we do? And this is precisely what we are doing at UCSB as well, is that a solution that we can opt for is to build or transform your campus network into a programmable research infrastructure that you can use to collect data for developing models and then also test these models in production settings, near production settings, right? So why is this important? So or in some sense, why campus networks at all? Any thoughts on why campus network is a decent choice for such a thing? Sorry, what? Yeah, you own it. Every research university has a network, right? And you own it. So there is some degree of flexibility in programming it rather than asking Google to make changes on their network so that you can collect data, right? Any other thoughts? Yeah, so you have representativeness on the campus network because you have so many users. In other words, I would also expand and say that campus network is a composition of different type of networks that you have studied so far, right? So we do have some data centers on campus networks. We do have residential users on campus network, and we do have these library or enterprise like departments, buildings, and enterprise like networks as well, right? So in some sense, I have a sample of residential network. I have a sample of data center, or I would say loosely I would say wide area network or like content networks as well. but also the enterprise networks, right? So there is a sample of different type of networks. I can pick and choose which type of network, which part of network I really want to focus on, right? Any other thoughts on campus networks being useful, meaningful here? Yeah.
Little like return for tax.
Yeah. Yeah. So you're like, they're interesting because even though you might think that, campus networks are, who will be interested in attacking a campus network, but a lot of them are. So there is always a lot of interesting traffic coming in and out of campus networks. You're saying something.
Oh, that's a graphic.
But so another thing that I would add is that, like even though we are interested in scale of the problem, right? Like we are interested in building things that work for hundreds of Gbps or maybe terabits of traffic workload. But a good thing about campus is that it's relatively small scale, right? Which is good and bad, right? I mean, like, maybe I won't be able to understand how my model is going to work when I'm getting 100 Gbps or 1 Tbps of workload. Maybe I will not get that type of workload here. But it also means that, like the type of data that I'm getting here, it is a bit manageable compared to, say, Verizon, where I'm always getting Tbps of traffic workload, right? So this scale is good and bad in a sense. It's bad because you might not get this full spectrum of test scenarios that you really want to take into consideration, but at the same time, it makes this setup a relatively more manageable. So there are certain design principles that one has to take into consideration. That one, if you try to do anything on campus network or anything on production network, you need to make sure that there are no disruptions, right? So whatever design choices you make building this type of network, you have to make sure that you're not disrupting any of these campus services or any of the users, right? Second, obvious point, preserve user privacy, right? Like nobody will approve any research agenda that is compromising user privacy, right? So that has to be a primary design principle, that whatever you do, never leak, never compromise user privacy. And the second theme of design principles are more related to the democratization. And this is something that I made point earlier, that this whole point of process is not to make sure that we collect the right data at UCSB, but more importantly, we build software that can be replicated across all different type of campus networks so that everybody can collect their own data and road test these type of models on the network, right? That is a bigger objective here, rather than just being used, like making UCSB capable of doing this type of research, right? So it's very important that we use, or we make design choices such that we are only leveraging off-the-shelf servers, keeping the cost as low as possible. We are minimizing the storage and compute costs, right? I can come up with a solution that requires me to, like store hundreds of petabytes of data. It is possible at UCSB because we have contract with Google that gives us access to that type of data storage, but not everybody will have that type of resource, right? So I really need to focus on making sure that whatever design choices I make, whatever solution I propose, it is feasible, manageable by a lot of diverse set of campus networks out there. So as I said earlier, that collecting data is, or collecting the right data is very critical in this context. And the easy thing that I can do to collect fine-grained network data is to start collecting packet traces, right? And I can focus on the border router at UCSB. Remember, border router is the one that is peering with the external provider, and all the traffic in and out of UCSB is going through that border router, right? So if I want to collect network data at fine granularity, all I need to do is to put some configuration that will mirror the packets from border router, send it to my collector where I can process those packets and put that into storage, right? And then I can do whatever I want to do in terms of analysis. The only hole in that argument is that, one, it's going to be a nightmare scaling such a pipeline for all the reasons that we have discussed so far in the class about the telemetry systems in general. And also, like if I just mirror all these packets and keep all those packets to store all those packets, I'm just, I'm just waiting for someone to launch an attack and take away all the privacy sensitive information from the user traffic, right? So I really need to focus on the privacy issues, and I really need to focus on the scalability issues. So I think, like, maybe in the interest of time, I'll skip a couple of these next slides, which I will cover in the next lecture. But I will focus, zoom in on. Yeah. So I'm skipping a couple of slides, but I'll get back to these slides once we understand the bigger picture. We'll come back to the specific details of how we do that. But so like I was saying that we need to collect packet traces. What we can do is that we can use a PISA switch, right? That we have all known so far. What we will use PISA switch for is to enable anonymization at line rate, right? And again, this is something that we will go in detail later. But what I mean by that is that users, when it comes to user traffic, payload is a big no, right? You should not be handling payload because most of the time it is encrypted. So from machine learning perspective, it's not very useful anyways. But payload in general can have a lot of privacy sensitive information, especially if it is unencrypted. You don't want to deal with that, right? So most of the machine learning use cases that we're talking about, packets headers are good enough, right? So one thing that we can use PISA targets to do is to strip away the payload from the packet, identify just like write a parser which extracts all possible packet fields, convert that into a output packet which is just carrying the header fields, right? And I can also anonymize the header fields as well, right? So what do I mean by that, right? So now that you know how P4 works, it has a parser, it has a deparser. So what I can do is that, but anyways, these packets that are coming to me from the border router are mirror copies, right? So even if I drop them, I do whatever with them, it's not affecting the user experience for the first thing, right? So these are cloned versions anyways. Now, when they come in the PISA switch, then my goal is to, one, make sure that I identify or, I parse the fields that are of interest to me, which go as low as the layer 4 header fields, right? So go extract Ethernet frames, extract the IP layer, and then extract the transport layer, which is UDP or TCP. Once I do that, then whatever is below the TCP, and we know how we can write those type of programmable parsers, whatever is below TCP, we just ignore it. And then at the typically at the deparser, when you do all these type of transmissions, the deparser, the payload is added back. But you can specify in P4 program and say I don't really want that payload with me, right? In fact, you can go one level up and say okay, maybe I can process or place these header fields in a way that is more amenable to analytics task later, right? So rather than requiring any type of further processing in the user space, I can create a data set or these set of tuples of the packets in the data plane layer, data plane itself, such that the output is basically a tuple. And the output that I will eventually get is basically a CSV that on which I can apply whatever analytics task I want to do, right? So this is all possible in the PISA switch, and if time permits, this is something that we can discuss in the last discussion section for you to understand how these type of pipelines are realized. Another important thing is that we can technically anonymize packet headers at line rate with PISA switches, right? So what I mean by anonymize, that when we talk about packet headers, there are certain type of packet headers that are privacy sensitive, certain type of packet headers that are not so privacy sensitive. Say for example, what we really don't want any user or any researcher at UCSB to know is that which specific IP address this traffic is coming from, right? So I want to definitely anonymize the source IP address or the destination IP address. If it is incoming traffic, then the destination IP address. If it is an outgoing traffic, then the source IP address, right? So how can I do that? I can do that by parsing the IP address fields and then apply some type of randomization of a certain portions of those bits, right? I can make one choice that I have is that maybe I can just randomize all 32 bits of the IP address, right? But then I will, if I randomize the entire 32 bits, then I just lose the semantic meaning of that IP address, right? So it's not important for me to know that it is coming from you or you, but maybe it is important for me to know that it is coming from this building, right? So the building level mappings are available at the prefix level granularity, right? So in some cases it is /24, that the first 24 bits are telling me that this traffic is coming from this specific building or Harold Frank Hall. And then the last 8 bits are telling me that it is coming from you or you, right? I can randomize those last 8 bits, but preserve the first 24 bits, right? So that way I'm not losing the semantic meaning that is encoded in the packet, but at the same time I'm preserving specific users' privacy, right? And the other field that I can focus on is the MAC address, right? especially, like the user's MAC address is, and depending on how the network is provisioned, maybe I won't see the user MAC address at all, because MAC address is a layer 2 feature, right? So unless I am, like one hop away on the layer 2 network, then I won't see the user's MAC address, right? But in case, assume that, like this is a bit more broader setup, not just UCSB, and there are cases where the vantage point from where you're collecting the data is just one hop away from the actual users, then the MAC addresses of those users might be a bit revealing, right? Because I don't know if you folks know, but the first few bits of the MAC addresses are always unique to the vendors, right? So looking at the MAC addresses, I can always tell that whether this traffic is coming from an Apple device or an NVIDIA or Dell or whatever, right? So this is a bit like, this is useful information, and then I like maybe I want to preserve that, maybe I want to anonymize that, but definitely I don't want to preserve the entire specific MAC address of the user, because that's something that can be revealing the privacy of the user significantly, right? So this is what we can do using these PSA targets. We can anonymize the headers, we can strip away the payload fields, and also we can like load balance the traffic, right? So if the traffic is coming in at 10 Gbps and I have a switch which probably has 30 something ports, then I can divide that traffic across 30 different ports, randomize or like load balance that traffic across 30 different ports. What that will entail is that every port or the traffic that the server downstream is handling, the amount of traffic that it needs to handle is 30 times less than the original traffic, right? Which means that I like the CPU load at each of the cores that are handling the traffic is going to be significantly low, right? And this is something important from the democratization argument perspective, that our design principle is to make things or keep things as cheap and as requiring as less specialized hardware or software as possible, right? So if I can, for a 10 Gbps traffic, I can reduce the amount of traffic that one single core has to handle to as small as 100 Mbps or 20 Mbps, then I don't really need a specialized hardware or specialized server for that. I can just use, very, very cheap. Like I can even use Raspberries, which are $100 to handle traffic that is as small as 30, 40 Mbps, right? So this is the value of hardware target, being able to load balance the traffic across the ports that it has, right? Any questions so far? Okay. And for the problem that I was mentioning, and the slide that you are looking at here is basically exactly how we collected the data for the example that I was discussing earlier, that I need some type of samples. I need some type of labels for the data. So for the security problem that we were talking about earlier, I can use Suricata. Suricata is an open source software, and it is used to implement the intrusion detection systems or IDSs. And this is something which is production quality stuff, right? So this is exactly what Verizon uses in their production network as well. UCSB does not use that. UCSB buys a proprietary solution. I don't know why, but which always fails, by the way. So, but this is something which a lot of production networks use. So we can use them, we can run them. In some cases, we got the subset of rules that Verizon was using. So we were kind of like ensuring parity in terms of type of rules that are relevant for production networks versus the type of rules that are relevant here, right? But notice here, just one second. So the notice here that I am sampling packets when I'm trying to label, right? Because if I try to label each and every packet, then I will incur a significant compute cost, because then I have to process all the packets coming in and out. Like, the same, it will be a bit of a reverse logic that I was saying earlier, that I'm saying like, I want to reduce this. So, but I'm not capable of, and technically I'm not capable of. Maybe at UCSB, I can buy a bunch of servers and make sure that I can handle 10 Gbps stuff. It's not a lot, but in principle, we will not be able to scale this type of pipeline up, right? So we really need to think about principal argument where we can make sure that we have a pipeline where we are sampling, and then it is a bit of an intelligent logic that has to be embedded into the system, which figures out that what is the right data to sample. You have a question?
AI based on labels from
for the reason that I just said, right? So because we cannot scale the packet processing with Suricata, so I can use Suricata to sample or label a subset of traffic. Yes. Like the equation here is that, 3 racks of servers are required at Verizon to handle traffic from, sorry, 1 rack of server is required to handle traffic from 3 racks of servers at Verizon. So every traffic that is generated by 3 racks of servers at Verizon's, like internal data center network, we just require 1 rack of server of IDS to implement all these type of rules and signature checking, right? So it's a prohibitively expensive thing to do. And as I said, right, like I cannot label all data, but I can label some subset of data. The research question that eventually needs to be answered is like, what is the sampling strategy that I should use such that I can train these robust machine learning model and not get skewed by what are the problems with the other set of papers as well. So so far, like, the labeling process that I explained with Raspberry, with Suricata is only applicable for the that specific security problem that we were talking about, right? But then, there are so many machine learning use cases that we talked about, especially we talked about quality of experience optimization as well, where the problems are, say, classification related, inferring quality of experience, or coming up with these, RL-based policies for packet scheduling. If I want to collect the information for these type of use cases, I need ground truth, which are in a lot of cases that ground truth is only available at the end host, right? So for example, when I talk about YouTube or Netflix, the ground truth for me is the quality of experience for the user. But this information is only available at the user, right? So if I want to, like label the YouTube traffic and attach some quality of experience labels for that type of traffic, I need those labels from the user, right? But then, if I go out and try to recruit all of you to maybe install my app so that you can share your quality experience labels with me, I don't see that path being feasible, right? One, there are so many challenges. Then we have to deal with privacy issues, and then we have to deal with building systems that work on Android, iPhone, MacBook, Dell, all those things, right? So people have tried that, but that's something which is really, really hard to scale. I might be able to lure maybe 10 of you to do that, but I can't get hundreds of thousands of such users out there, right? So what we can do is that or what we are doing here is that we are actually deploying bunch of Raspberries on the campus, right? So Raspberries are these single board computers that are extremely cheap. When I say extremely cheap, these are like $100 devices still. But relatively speaking, these are very cheap devices, right? I can buy thousands of them and then deploy them on campus, and that will provide me with a very, very unique data set or framework where I can just programmatically specify, okay, right now I want to collect YouTube traces from the device that is in this room, right? And that might not tell me what exactly is the user experience that you are having. It might be a proxy for the type of user experience that you will have if you're running a YouTube at that time, right? So this is giving me some labels. Again, I will not be able to label each and every packet trace that I see on the campus network, but at least for a subset of data, I will have that type of flexibility. And finally, we talked about the requirement that we should be able to deploy machine learning models in a programmable manner. So, I should be able to deploy a machine learning model at different vantage points. Maybe I want to test how this model is going to work if I'm executing that on the border router, or if I'm executing that at the access point on the Raspberry itself, right? So there are these different locations or different setups that I really need to take into consideration. And like depending on the type of machine learning model, the type of scalability it offers, there might be different vantage points or locations it can be deployed, right? So overall, I think what this is motivating is that so far I'm telling you bits and pieces that if you want to collect data, we can use pizza switches. If we want to collect labels, we can use Raspberries, we can use Suricata. But if I ask any of you that, okay, you want to work on developing a machine learning model, here is what we have, just go figure it out, right? Then you will be overwhelmed with the entire process here, because now you have a P4 based target that you have to program. Then you have a Raspberry that is like Linux system. Then you have maybe access points. Then maybe you also have some routers that you have to deal with. So there is a lot of complexity in terms of letting the users write these low-level programs of how they can collect the data and how they can deploy these models, right? So what we really need to offer is a higher level of abstraction, right? And this is in line with what we have been reading in the software-defined networking in general, that whenever you're talking about building these systems, you always have to reason about the abstractions, right? If I let the programmers or users write the P4 program so that they can collect the data for different type of applications, then it's a low level abstraction, right? I will take one level abstraction up and say like, okay, let's make this abstraction of the API completely agnostic to the type of targets that are out there and focus on what's most important. What's most important for me is to get data, to get label, and deploy models, right? These are the three things that are most important for me. What I really want to specify for each of them is that what I want to collect, when I want to collect, where I want to collect or deploy, right? So an example can be that maybe I want to specify a policy or a rule which says like, okay, I want to collect quality of experience labels, such as the resolution or the bit rate and all those things from YouTube application, from library as a network condition or as a network location, only when the latency inflation is more than 20 milliseconds. Now, this last part might be a bit tricky for you, but just to give you some perspective that when we talk about these campus networks or in general last mile networks, latency is an important factor, right? Like, it plays a huge role in terms of, type of bandwidth you're able to achieve, and like, is a good indicator of congestion in general. So we have, like there is a separate line of work where we're trying to figure out ways in which we can compute this latency using the packet that we see in the network itself, right? But the point is that in general, most of the packets on a campus network should not see more than 5 to 10 millisecond latency, right? So if any of them are seeing more than 20 millisecond latency, that is an interesting data point for me, because most likely these packets are getting queued, like, are facing congestion, are getting queued at some of these devices. Maybe this type of queuing is happening at the access point. Maybe this type of queuing is happening at the building router itself. I don't know, but if I see this type of high latency, then for me that is an interesting traffic, right? And this is in line with what I was saying earlier, that I might not be able to label each and every traffic on the campus network, but I might be able to specify that what is my policy for collecting these labels, right? So if I see this type of behavior, then that's when I want to collect a QoE label for this specific application from this specific location. And similarly, I can specify using this type of abstraction and say like, hey, I want to deploy Net Microscope. For reference, Net Microscope is a state-of-the-art machine learning model that is trying to infer the quality of experience labels or quality of experience from encrypted traffic, right? So think about YouTube, Amazon, Twitch, and all those things. It just looks at the sequence of encrypted packets that correspond to this application, and then infer what is the like the resolution that you're looking at, what is the buffer size, is there any rebuffering that's going to happen and stuff like that. So these are the things that it is able to infer. So I can specify that, hey, like this is the state-of-the-art model. I want to understand how it performs in my network. Then I can specify that, okay, let's deploy it at the border router, because I say border because it means that I'm forcing it to work in a much more intense setting, that it has to handle 10 Gbps or 20 Gbps of workload, right? And I want to maybe specify a residential network, because those are the type of networks that I really care about, because those are in some sense proxy of a cable network or any type of last mile network, right? So I can do this type of sampling and say like, okay, if I want to understand how does Net Microscope perform in any type of home network scenarios, then I can push this type of thing, and this might be an emulation of what a cable network might be able to do as well, right? So this entire discussion that we had about the programming abstraction, our goal was to make sure that these programmers are able to express their intent without worrying about what type of target this is to run, right? But somebody has to do that type of translation. And this is similar to the virtualization layer abstraction that we were, or a specification abstraction that we were learning about software-defined networking, that we just abstracted away all the target specific details from this framework in the programming abstraction, but we still need some type of layer that is going to translate those high-level programs that you have expressed into the low-level configurations out there for these devices, right? So, if I express, let's talk about this, that I'm saying that we are going to collect QoE labels for YouTube from library, inflation latency greater than 20 milliseconds. What really needs to be done here? It means that I need to run some queries using Sonata on the hardware target or on the piece of switches to identify which set of IP addresses have a latency greater than 20 milliseconds, right? Then I need to figure out that, okay, where are these IP addresses? and for like which are those IP addresses that are in the library. And then I need to figure out where those Raspberries, like what type of Raspberries do I have in libraries, and then start collecting the data from there, right? So in some sense, for just this simple type of query or simple type of task, I need to program a PISA switch, I need to program a Raspberry, and I also need to program the data collection pipeline in general, which is going to generate the labeled data set for me, right? So there are so many elements and components that need to be programmed, rather than requiring the programmers to directly write P4 programs and the program for the Linux or for the Raspberry itself. We just let them write this high level of abstraction, high level program, and then let the virtualization layer translate all these high level programs into the device specific commands and configurations, right? So this is kind of like the bigger intent of the system, that we are simplifying how you can generate and curate this type of data. So I guess we are getting to the end of the class. So I'll try to make sure that I cover these 2 points clearly. That what I was explaining you is the type of infrastructure that we are trying to build at UCSP, which is replicable across different networks, right? And we have been developing this at UCSP, but we have also been helping universities like Columbia, Princeton, University of Chicago, and University of Oregon to deploy similar pipelines in their networks as well, right? And what that has enabled is that it is enabling very fundamental research in this area, right? So for example, the traffic of interest problem, where we are trying to identify benign traffic or malicious traffic as traffic of interest, we observe that there are these specific spatial and temporal behavior that is exhibited by the traffic, which the synthetic packet traces will never capture, right? So for example, when we think about an intrusion detection system, every time a new packet comes in, it just assumes that the likelihood that this can be malicious or not is random, right? It can either be malicious, it cannot be malicious, because it has no context about where this traffic or packet is coming from. But what we observed in our research is that, depending on which set of prefix this packet is coming from, is it coming from Amazon AWS? Is it coming from UCSB? Is it coming from Princeton? Depending on the history of behavior that was exhibited by different prefixes, different organizations, I can associate some probability and say like, okay, if it is coming from AWS, I should be careful because, like all these attackers launch, when attacks are launched, they use AWS and GCP and all those type of platforms, right? So if it is coming from some type of cloud prefix, I will be careful, right? So I'll have a different likelihood of that. Burstiness is also that, I don't really want to, put all traffic from AWS and GCP on hold forever, right? So we observe that, whenever these things happen, whenever a malicious behavior happens, it happens in a burst. So if I have not observed any malicious activity in the past, the likelihood that this will be malicious in the future, as we keep on increasing good, or as we keep on observing good behavior over time, is low. So we can actually leverage these type of observations to come up with completely new set of features that nobody thought about before, because they were just working with the synthetic data that is just missing out on all these real world insights, right? So this is one way in which this type of infrastructure is enabling fundamental research, but that it is enabling us to identify new features that people didn't thought about before. And the other 2 points are something that I made before as well, that using these type of data, we are able to develop new tools to understand how different machine learning models are making their decisions. And based on that, we are able to identify that, okay, a lot of network security, machine learning based artifacts for network security, they're either victims of shortcut learning, things that we discuss here, or they're just learning some spurious random relationship between the data and the output, and they just don't generalize. And or we also see that these type of models might work for one type of distributions, but not for the others, right? So in some sense, they're just overfitted to certain type of distributions, and as soon as those distributions change, then these machine learning models just fail, right? So I kind of gave you an overview of what this platform is capable of doing, how is it supporting fundamental research, but I also want to put a caveat here that this problem is far from being solved, right? What we, again, like Sonata, this is just a step in the right direction, but it's not the full solution. The problem of scalability still exists. I can maybe, with all these optimizations that I'm able to do, that, remove the header fields, load balance things, I might be able with set of resources that I have, I might be able to make sure that I can continuously collect this data for 1 week. and then I have to stop. I have to refresh the system and then load the data on Google Drive or whatever, and then repeat the process. But then I cannot guarantee that I can continuously collect this for months or years, right? This is something that I cannot support, which is technically, when I say longitudinal, this is something important, because we are really focusing on anomalies in most of our cases, and anomalies are always rare by definition, right? So we really need longitudinal data collection, and we don't have solutions for that. Another thing is that, even if I have this infinite amount of storage from Google available to UCSB users, I have terabytes or maybe petabytes of data sitting out there, which I don't have resources to process, right? To process that amount of data, I need, maybe massive amount of compute farms to do that. Or I need to, just make a decision that, okay, only if I have some external insights, I would, query that data. Otherwise, that data is just sitting there, maybe useful in the next 5 years or something. But right now, we're not capable of processing that data unless I decide that I'll spend $1 million on Google Cloud and use their compute resources to process all that data, right? Otherwise, that data will just sit out there and I won't be able to do anything. So there is a very strong use case for how can we, develop new tools that are, like maximizing how much processing is possible with this petabytes of data, right? Like in general, network data is always intense in terms of scalability. So this is just motivating. Maybe can we use piece switches to expedite the processing that we got, the time it takes to analyze the data, petabytes of data for networking traffic, right? So is it possible for us to come up with some solutions where we can use piece switches which are offering this fast packet processing capabilities to scale up the analysis of the data? Otherwise, we can collect all this data, but we cannot analyze all this data, right? And the privacy stuff is important as well, that I mentioned about the anonymization that we can do. That's good enough for UCSB researchers, because I still have some context about where this network is. There are still possible leakages that can happen, but we don't know. So I don't there is no way I can share this data in public domain. I cannot just say like, okay, hey, we collected this UCSB, here's the data, you also do the same research and maybe tell us how it looks, right? This is not possible because there are still a lot of legal implications if I try to share that data in public, right? So there is a lot of work that needs to be done in which, tens of different campus networks collect this type of data, and then we figure out ways in a privacy preserving manner that we can use all that data to ensure robustness in the machine learning models that we're trying to build without moving the data, without actually sharing the data with each other, right? So there are a lot of work, this is not my area of expertise, but there are a lot of researchers who are working on this specific problem where you can ensure privacy preserving analytics at scale, right? All right, so I should end the lecture now. That there are a few takeaways from today's lecture, that AI machine learning for networking is a real thing. It's happening. It's happening at Google, Amazon, and Microsoft, and all these type of companies that you can imagine here. But as researchers in academia, most of us are not ready for this wave of innovation, and this is problematic in many ways. The idea that we at UCSB have been exploring is that we are trying to transform our campus network into a programmable research infrastructure that we can use to collect this high quality data that we can use to train machine learning models, but also use it to test these models in production settings or realistic settings. And finally, the system that we have is enabling development of trustworthy machine learning models that we can have, confidence deploying in production networks. But still, there are a lot of problems related to scale and privacy that still remain unsolved. Okay. So with that, I'll end the lecture. So tomorrow's discussion section will focus more on, Sonata part, like how we can compile those type of queries in P4. And the next lecture will focus more, or the next discussion section will focus more on the first part of the pipeline that I was talking about, that how we can use these hardware targets to anonymize, load balance the traffic, right? So we can show you how exactly these type of programs have been developed at UCSB that are enabling us to scale the data collection. Okay. All right. Thank you all.